Hi. So today we will be learning dipole and electric field due to dipole. We have electric charges in whole our surrounding, in whole our atmosphere. And these electric charges are present here in 2-3 forms. There is one form, there is continuous distribution of electric charges on any object. This is one way how electric charges are present there in our surrounding. Now second way in which electric charges are present is in the form of dipole. In the form of dipole, we know we have matters made up of molecules. And each molecule has equal number of positive charge and equal number of negative charges. So on the whole, molecules are neutral. Now, if the center of all the positive charge and center of all the negative charges are separated by small distance, center of positive charge and negative charge, then they form a dipole, then they constitute a dipole. So what is a dipole? When the center of all the positive charges and all the negative charges are separated by some distance, then they form a dipole. Okay. We have so many examples. Water is one such example of dipole. HCl, H2SO4, so many other. Now these are very special molecules. They have net charge they have charge net is equal to 0 because all the positive charges plus all the negative charges and they form net charge is equal to 0. But they have electric field. Electric field net is not equal to 0 as at different points as according to superposition principle at different points they do not cancel each other. Electric field due to positive charge and electric field due to negative charge at different point in the space, they do not cancel each other. as obtained by superposition principle. Due to positive charges and negative charges. Positive charge and negative charge do not cancel each other exactly. So, most importantly, net charge is 0, but electric field is not 0. There is electric field. So, dipole becomes very important, and it has very important properties, and very important applications also. In various fields, it has application. Now, let us learn about non-polar molecules. Like O2, H2, they have net charge. Charge net is equal to 0, and also electric field net is equal to 0. But when you place a non-polar molecule in external field, external electric field, then it will behave differently. On placing in external electric field, like this, in this very figure, you have external field, E external. So a non-polar molecule is placed in external field, then its positive charge and negative charge will experience force in different directions. Force on positive charge will be in negative, electric field direction. Negative electric field direction. Oh, I'm sorry. Okay. Force on positive charge will be along positive electric field, yes, because when you place a positive charge in any field, then it experiences force along the electric field. Force along the electric field. Okay. So force on positive charge will be in the direction of electric field. It will, due to the influence of that force, it will be moved along that direction. And force on negative charge minus Q will be in opposite direction of electric field. So negative charge will be displaced along this direction. So the two charges are separated. You can see positive charge experience force in one direction and negative charge experience force in another direction, and due to this the two charges are separated. Forming a dipole. So generally we have dipoles only. All along. Now we have to find electric field due to such dipoles. So before finding electric field due to a dipole, let us first know what is a dipole and what is a dipole moment of this dipole. So dipole, when two equal and opposite charges plus q and minus q, two small equal and opposite charges are separated by a small distance. Let the distance is 2l. Distance is from center here in one direction l and here in other direction l, so distance is 2l. So such arrangement of charge is called a dipole. Two equal and opposite charges separated by a small distance then they form a dipole. They form a dipole, and now this dipole has some moment. When you place a dipole in an external field, then it experiences some torque, and due to that torque it has a rotational movement. It tries to rotate and it tries to align in electric field, so it is having some dipole moment. So let me define dipole moment. Dipole moment is numerically equal to product of, okay, let me omit this, okay, equal to product of any one charge, any one of equal charges and the distance between the two charges. Two charges, okay. So, and dipole is a vector quantity. As it is experiencing a torque, obviously the two quantities, electric field and dipole moment, must be vector quantities. So dipole is a vector quantity. Dipole is a vector quantity. And its direction is from negative charge to positive Now recall that electric field has direction from positive charge to negative charge. Electric field has direction from positive charge to negative charge. But here dipole moment has just opposite direction, from negative charge to positive charge, is equal to P cap late. Let us assume that unit vector is, let us assume that unit vector is P cap, okay. Therefore, dipole moment has symbol P. Dipole moment has symbol P. So dipole moment is equal to any one charge into distance between the two charges and unit vector along the direction of dipole. therefore P is equal to 2Q. Okay, let me omit this. Okay. 2QL into P cap, directed from negative charge to positive charge. Okay. So remember that electric field vector is from positive charge to negative charge, but dipole moment is from negative charge to positive charge, just opposite. And its unit of dipole moment is equal to, for charge it is coulomb and for length it is meter. So coulomb meter is the unit of dipole moment. Now let us find electric field due to a dipole. Electric field due to a dipole. So we will be finding electric field at a equatorial bisector plane. Second one, axial point. Number one, at an axial point. Number two, on a point at the equatorial bisector plane. And then at one general point, at a general point. So let us find electric field due to a dipole at these three points. So first of all, let me do first question number 1. So let me take one dipole. There is a negative charge minus Q, there is a positive charge plus Q, and an axis passing through these two charges. The length of dipole is 2L, okay. And from center at a distance R, we have a point P where we have to find electric field. Okay. So we will use principle of superposition. For finding electric field, we will find Coulomb's law, and then we will use principle of superposition. So according to Coulomb's law, field E due to negative charge is equal to K Q upon R square, and here R changes, here R, okay, let me omit. Here distance is from minus Q to, okay, here distance is from here to this point, and this is equal to R plus L. So distance will be R plus L whole square. Okay. And the direction, here if you place a positive charge, it will be attracted here. So force will be along negative of dipole moment direction. आपका डाइपोल मोमेंट डायरेक्शन है माइनस क्यू से प्लस क्यू इस साइड में, लेकिन अगर यहाँ एक छोटी सी पॉजिटिव चार्ज रखते हो पॉइंट पी पे, तो इस पे माइनस क्यू की वजह से फोर्स जो है अट्रैक्टिव इस डायरेक्शन में लगेगा, इस डायरेक्शन में लगेगा। तो हम क्या देखते हैं कि डाइपोल मोमेंट के अपोजिट ये है, इसीलिए हमने लिख दिया माइनस पी कैप। सो लेट मी omit this. Okay, now electric field due to plus q charge, and this will be k q upon, and this distance from q to p, this distance, and this distance is equal to r minus l whole square. And if you place a positive charge near to this positive charge, then it will be forced in outward direction, and this direction is same as direction of dipole moment, that is from negative charge to positive charge. So direction is same, so it will be plus p cap. So these are the two electric fields. Now using superposition principle, when you use superposition principle, you know that we have two laws for finding electric field. So one law I used Coulomb's law. Now second one is on using principle of superposition. So therefore E net is equal to E due to minus Q plus E due to plus Q, and this is equal to KQ upon R minus L whole square minus KQ upon R plus L whole square, and the direction is P cap direction. So this is equal to E net is equal to, let us take out the quantities which are in both the terms, that is KQ into 1 by R minus L square minus 1 by R plus L whole square into P cap. And now let us simplify this. So let us take LCM. So this will be equal to product because they are different. So let me multiply the two, a plus b into a minus b. This way we can multiply it, and it will become equal to a square and whole, because both have power 2, so whole power 2. And here it becomes r plus l square minus r minus l whole square, and direction is p cap. Therefore electric field net is equal to KQ by, and above it is equal to R square minus R square plus L square minus L square plus 2RL, and this is minus into minus 2RL, and this is R square minus L square whole power 2, and this is in the direction of dipole moment vector. The R square are cancel, L square cancel, therefore E net comes equal to 4 KQ into 4RL divided by R square minus L square whole square P cap. Now we know that 2QL is dipole moment, so we can write K into 2 into dipole moment P, and 2 into R is remained and divided by R square minus L square whole square P cap. इसको फिर से हम देख लें जरा। इसमें से जो 4, ये Q है, दिस इज Q, तो 4QL में से 2 हम निकाल दें, 2 यहाँ है, तो हमारे पास बाकी बचा रहता है 2QL and 2QL is equal to dipole moment and R is here. So everything I have written. So okay. So this is your electric field net. This is your electric field net. Now suppose this R is, if you have this R, आपका जो ये R है, it is if very greater than length of dipole. Since dipoles are very small, the molecules are very small, so their size L is negligible. So here, if you have R very greater than L, then you can further simplify electric field. Electric field net will be equal to K2P upon, just neglect L, so it will become R power 4 and here R and P cap, and one R is cancelled, so you find that electric field net is equal to K2P upon RQ P cap. Upon RQ P cap. So this is the electric field due to a dipole in axial direction. Not two. Electric field at a point on, okay, let me okay, on an equatorial bisector plane. Okay. Let us first of all take a central line and not a plane, and let us find electric field on this line, on equatorial bisector. Better we should write line, equatorial bisector line. At a point P, here we have to find electric field at a distance R, and the dipole is having length L and L. Here is your minus Q and here is your plus Q. So this is the schematic diagram, and from here we will be using the same two law, Coulomb's law, and another is superposition principle. So let us find electric field separately by the two charges. So electric field due to positive charge, and we know that it is along radially outward direction, along this direction. So electric field due to positive charge will be equal to K into Q upon square of this distance. Means this is hypotenuse. Hypotenuse is root under length square plus base square. So square of it becomes equal to R square plus L square only. Squaring, we just remove the root. So this is in the direction of, okay, let me take here point A and here point B. So this is in the direction of BP cap. This is the direction. Now electric field due to negative charge, and you know that if you place any positive charge at this point P, then it will be attracted towards negative charge. So electric field direction at this point due to this negative charge will be along PA. So firstly let me write magnitude of this electric field. So this is equal to KQ. I am writing many magnitude. So I will not be writing its sign, okay. So KQ upon, and the distance is same, R square plus L square, and it is directed from P to A, so PA cap. So 1 and 2, we have two electric fields. Now to find the resultant of the two, using superposition principle, net electric field net is equal to E1 E positive plus E negative. Now let us see that the positive charge, electric field due to positive charge, it will have two components. One component will be in the direction of, which direction? It is direction opposite to dipole moment direction, in this direction. And electric field due to positive charge will have one component along perpendicular direction. So this is your x component, and this is your y component due to positive charge. So we have just, I have resolved electric field due to positive charge into two components. Now similarly, I will resolve electric field at point P due to negative charge Q into two of its component. So we will find that one component will be along electric field component due to negative charge along x direction will be along negative of dipole moment, because dipole moment, as we learned, that it is from negative charge to positive charge in this direction. But here one component of electric field is opposite to this dipole moment direction, and one component will be vertically downward direction. So what we see? We see that the two vertically opposite electric field components that are equal, they will cancel each other. Okay. So here in diagram we can see that the electric fields that have two equal and opposite vertical components. So they cancel each other. Okay, let me cancel it. So they each other. Okay. Now net electric field will be along negative of dipole moment direction. Okay, so therefore E net and let one more thing. It is, suppose it is making this angle. Okay, this angle is theta. Then alternate interior angle, this angle will also be theta. And since the fields are equal, so net field will be just dividing the two angles, and this angle also will be theta. So E net will be equal to, therefore E net will be equal to E due to negative charge and cos theta. E due to negative charge cos theta plus E due to positive charge and cos theta, and this is along minus P cap. So let us find out. So this is equal to electric field due to negative charge, and it is equal to KQ upon I square plus L square and cos theta. Let us write the value of cos theta. Cos theta is equal to base by hypotenuse, and base is your L. Base is your L by hypotenuse is root under R square plus L square. This is your cos theta. Plus EQ also is same, KQ upon I square plus L square, and cos theta is same, L by root under R square plus L square, and this is directed along P cap. This is directed along P cap. Now E net is equal to minus, let us take common quantities K, Q, L, all are common, into 1 plus 1, it is 2 times, and this is also common, R square plus L square whole power 1 by 2 plus 1, and this is along P cap. Now therefore electric field net, let me write vector notation, okay, is equal to minus K2QL divided by I square plus L square whole power 3 by 2 along minus of dipole moment vector, and this becomes equal to, electric field net becomes equal to minus K, and this is your P, divided by R square plus L square whole power 3 by 2 P cap. Now this is your electric field. Now if L is very less than R, so we can just ignore L. Therefore E net is equal to minus Kp upon R square whole power 3 by 2 P cap, and this part 2 is cancelled. Therefore E net we obtain at equatorial line at any point is equal to minus Kp upon R cube P cap. So we see that electric field is not varying inversely to square of R. Here electric field in the two cases is varying inversely to cube of R. So we can see that electric field in case of a dipole is quite different from electric field due to point charges, in which electric field happen to be inversely proportional to square of R. Okay, so let's define electric dipole in some different way. Electric dipole. We found that electric dipole, electric field due to electric dipole is inversely proportional to cube of R. So let us define electric dipole using this fact. Any charge accumulation which has electric field having inversely to cube of distance, inversely to, okay, let me omit this, inversely to, okay, cube of distance, when such charge accumulation, you can say a dipole, then called a dipole. Okay. Now we obtain electric field due to dipole at a general point. In the two cases we have found electric field due to a dipole in two particular directions, one in x direction, in axial direction, and other we obtain electric field in an equatorial bisector line. So now electric field due to a dipole at the general point. This is the third case that we have to do. Now let me draw first of all the diagram. So there is a dipole, minus q charge, plus q charge, and from center, which is at point O, we have to find electric field at a point P, which is at a distance R. Okay. Which is at a distance R, and this line is making angle theta with axial direction. Okay. So what will be the processes? So as we know that dipole moment vector is a vector. So this vector can be resolved in two vectors. Let us resolve this vector into two. So let there be a dipole moment vector along this direction of OP, and that will be OP cos theta. No, it is dipole, okay. So let me write, it is not distance, it is P cos theta, okay. Dipole moment, this dipole moment will have a component. I have just resolved this vector into two components. One is along this direction, and due to this dipole, you have electric field here along axial direction. Let that electric field will be E axial. Okay. And let us resolve this dipole moment in another component which is along this direction, and this is a direction perpendicular to OP direction. So dipole moment along this direction will be E sin theta. So we will be using the two concepts of axial electric field and equatorial electric field due to dipole. Therefore, electric field net at P is equal to electric field axial plus electric field equatorial. Now, for equatorial electric field, we learned that the equatorial bisector point electric field will be along negative dipole moment direction, in this direction. This is the direction of equatorial electric field. In previous case, in just case 2, we learned that electric field is in a direction opposite to dipole moment direction. So we have 2 electric fields and we have to resolve these 2 electric fields. This resultant electric field E net will be along this direction. Okay. So we have to find magnitude of this and we have to find direction of this. Suppose it is angle theta and it is making angle alpha. So for the vector we need to know only two things. Magnitude of the vector and direction of the vector. So firstly we will find magnitude. Therefore E net vector modulus of it, magnitude of it, is equal to under root E axial square plus E equatorial square, and this is equal to under root for axial it is K 2P, and here P is equal to P cos theta 2P, okay, 2P by R cube, and distance we have taken is R, so R cube plus whole square of it plus K P sin theta upon R cube whole square. This is magnitude, so we are not writing direction of it, we are writing only magnitude. Therefore, electric field net at point P, magnitude of it at P is equal to under root KQ upon RQ whole square into 4P square, okay, P I have taken already, KQ not KP, okay, let me omit this. KP I have taken outside, and here it is remained 2 cos theta, and square of that is 4 cos square theta plus, and here remained is sin theta, so sin square theta. Okay, therefore electric field net magnitude of it at a general point P is equal to Kp by upon RQ into root under cos square theta plus sin square theta plus 3 cos square theta. So I just expanded it and then I'll solve it, and this is equal to Kp upon RQ under root 1 plus 3 cos square theta. This is your electric field net, magnitude of electric field net at a general point. Now direction of this electric field. Direction of E. Since here in diagram tan alpha is equal to perpendicular by base is equal to E equatorial equal to perpendicular upon base is equal to E equatorial upon E radial and this is equal to, along equatorial it is equal to K equatorial, this is KP, and this is along equatorial it is okay KP sine theta, KP sine theta upon R cube upon K 2P cos theta upon R cube. So all the common terms will be cancelled, and this is equal to half tan theta. Therefore, therefore the direction of this resultant electric field innate will be at angle will be along an angle which is half of angle which is half of tan theta, which is half of tan theta. So from which direction? From radial direction, from the direction of R, from the direction of R means radial direction. So here we conclude. So let me conclude. Okay, so let's define electric dipole in some different way. Electric dipole. We found that electric field due to electric dipole is inversely proportional to cube of R. So let us define electric dipole using this fact. Any charge accumulation which has electric field having inversely to cube of distance, inversely to let me omit this, inversely to cube of distance, then such charge accumulation you can say a dipole. Then called a dipole. Okay. Now we obtain electric field due to dipole at a general point. In the two cases we have found electric field due to a dipole in two particular directions, one in x direction, in axial direction, and other we obtain electric field in an equatorial bisector line. So now electric field due to a dipole at the general point. This is the third case that we have to do. Now let me draw first of all the diagram. So there is a dipole, minus q charge, plus q charge, and from center, which is at point O, we have to find electric field at a point P, which is at a distance r. Okay. Which is at a distance r, and this line is making angle theta with axial direction. Okay. So what will be the processes? So as we know that dipole moment vector is a vector. So this vector can be resolved in two vectors. Let us resolve this vector into two. So let there be a dipole moment vector along this direction of OP, and that will be OP cos theta. No, it is dipole, okay. So let me write, it's not distance, it is P cos theta, okay. Dipole moment, this dipole moment will have a component. I have just resolved this vector into two components. One is along this direction, and due to this dipole, you have electric field here along axial direction. Let that electric field will be E axial. Okay. And let us resolve this dipole moment in another component which is along this direction, and this is a direction perpendicular to OP direction. So dipole moment along this direction will be E sin theta. So we will be using the two concepts of axial electric field and equatorial electric field due to dipole. Therefore, electric field net at P is equal to electric field axial plus electric field equatorial. Now, for equatorial electric field, we know that, we learned that the equatorial bisector point electric field will be along negative dipole moment direction, in this direction. This is the direction of equatorial electric field. In previous case, in just case 2, we learned that electric field is a direction opposite to dipole moment direction. So we have two electric fields and we have to resolve these two electric fields. This resultant electric field E net will be along this direction. Okay. So we have to find magnitude of this and we have to find direction of this. Suppose it is angle theta and it is making angle alpha. So for the vector we need to know only two things. Magnitude of the vector and direction of the vector. So firstly we will find magnitude. Therefore E net vector modulus of it, magnitude of it, is equal to under root E axial square plus E equatorial square. And and this is equal to under root for axial. For axial it is K 2P, and here P is equal to P cos theta, 2P, okay, 2P by R cube, and distance we have taken is R, so R cube plus whole square of it plus K P sin theta upon R cube whole square. This is magnitude, so we are not writing direction of it, we are writing only magnitude. Therefore, electric field net at point P, magnitude of it at P is equal to under root KQ upon RQ whole square into 4P square, okay, P I have taken already, KQ not KP, okay, let me omit this, KP I have taken outside, and here it is remained 2 cos theta, and square of that is 4 cos square theta plus, and here remained is sin theta, so sin square theta. Okay, therefore electric field net, magnitude of it at a general point P is equal to Kp by upon Rq into root under cos square theta plus sin square theta plus 3 cos square theta. So I just expanded it and then I'll solve it, and this is equal to Kp upon RQ under root 1 plus 3 cos square theta. This is your electric field net, magnitude of electric field net at